Okay, everyone, let's get started. So don't forget about the quiz that's due tomorrow by midnight. Make sure you log into Dropbox and take the quiz and submit it. Remember, you have two attempts, so you could submit one attempt, and it should tell you which questions you got right and wrong, and then you could take it a second time if you want, and the grade that's recorded is the second attempt. Okay, so be careful with that. Okay, so last time, just to quickly review, we talked about how you can design hardware using a behavioral description, which is equations or code, a structural, which is a block diagram of components, interconnected components, and then a physical design, which is where you allocate physical hardware for each of the components in the structure and then place them into the physical design somehow. In this class, we're going to be writing Verilog for the behavioral. The structural design you actually will not see very often. There is a way to go in and look at it, but it's usually not very meaningful for the types of designs in this class. They're so big and complex. It looks just structural design. Usually it just looks like a rat's nest. And then we're going to put it onto an FPGA. And I'm going to try to do a demo where I go through this today. We talked about abstraction, hierarchy, and regularity. And so this is important for you to understand because this is essentially how Verilog works, and HDLs, it's all based on hierarchies of modules. The idea is that you create modules that hopefully can be reused as much as possible, and then you create really increasingly complex designs by creating these hierarchy of modules that when you collapse the hierarchy, when you flatten the hierarchy, it's a huge digital design, but when you look at an individual file, for instance, it may not be that complicated, right? You may just have a few modules instantiated. So you can think of every one of the modules in a hierarchy as a logic circuit, and of course you used logic circuits in 2.11 in which you used digital logic gates. Logic circuits have inputs and outputs, and then they have some sort of internal implementation, as well as a timing specification, which we're not going to get to until later on. We're going to focus just on functional specification in this course. Okay, I mentioned too that so you've got a top-level interface with inputs and outputs. You can think of this kind of like a writing a class in Java with publicly accessible methods, and then internally you have modules that are instanced in there, generally speaking, unless it's a leaf node, and then there's internal wires that are declared internally, right? Kind of like private variables in Java. And then we talked about combinational and sequential logic. Combinational has no memory, sequential does. In combinational, you have to make sure that you don't have any memory elements in your design. In Lab 2, which hopefully the TAs introduced you to in Lab, you're going to be just making combinational logic, and I'm going to do a demo of that as well today and put on the FPGA. And then starting in the next lab, we'll end up having memory. I'd say memory for what? Well, we're building a CPU. We got to have memory to store the instructions, memory to store the register values, memory to store temporary values, part of the data path registers. And so, we'll very quickly get into sequential designs. We're going to be looking at a lot of block diagrams. Just keep in mind that wires are connected at T's, but not when they cross unless there's a dot. And SystemVerilog uses four-state logic, meaning that every bit in a bit string can adopt one of four values, 0 or 1, as well as X and Z. X can mean contention, meaning that you're double driving a signal. Z is high impedance, which means you're not driving a signal. Of course, 0 and 1 are just represent binary 0 and 1. I mentioned last time that you might see some stuff in the simulator that says strong 0 and strong 1, and as Philip pointed out, there's actually, I think, 8 different strength levels inside of Verilog. And the purpose of this is to resolve contention. So if you have a strong 1 and a weak 1, strong 1 and a weak 0, then the strong 1 will win, obviously. That's designed for modeling, though. That sort of stuff is not synthesizable. So in this class, we're focusing on synthesizable Verilog. We're going to focus less on modeling, trying to come up with, behavioral descriptions of actual hardware. Okay, and then as far as HDL goes, we've got VHDL and Verilog. We're going to be using Verilog, or specifically SystemVerilog, which is the latest version of it in this class. But they're both compatible with each other. And then we're going to be doing simulation and synthesis. Simulation is for testing. Synthesis is when you want to deploy your circuit. And I mentioned behavioral versus structural modules in Verilog. You can mix and match. Behavioral just means you're writing out behaviors, which are just going to be Boolean logic, arithmetic, or state machines. And structural is block diagrams, interconnections. Okay, so when we start looking at some Verilog examples, that should say, SystemVerilog example, because this logic type is actually specific to SystemVerilog. But this was a combinational, it was behavioral logic. First of all, it's behavioral because it's defining logic behavior as opposed to interconnected components that you're instancing. And it's combinational because there's no memory. I'm using a single line of code in here, which is called a continuous assignment statement. Continuous assignment statements are continuous in the sense that whenever any of their inputs change, anything on the right-hand side of the statement is considered an input, that will immediately trigger the output to be updated. So it doesn't matter what order you have this in your code. So you're thinking of this, now when you write a statement like this in Verilog, you think of that as a blob of logic that you're dropping in. So you've got a circuit that's driving Y, and so you don't want to drive Y with anything else, because this one statement has control at Y. Okay, so if you assign Y in another line of code, you're going to get contention, potentially. So this guy owns Y. He's providing the voltage on Y, and that is a sort of a concurrent blob of logic that will get synthesized. That statement will get converted into gate somehow by the synthesizer, the compiler. Okay. And then when you simulate it, you're going to generally look at this as a timing diagram. Where the horizontal axis is time, and then you'll have ones and zeros there, and then you have a cursor that you can move around. In this case, we're looking at every possible combination of inputs and the corresponding output. Because it's combinational logic, when you test this circuit, you're looking at the instantaneous values of the inputs and the outputs, because it's combinational. There's no memory involved here, so we're just looking at whatever the output is, and then there's corresponding inputs for that at that moment in time. And then we talked about some syntax stuff. I don't think that won't come as a surprise to any of you guys. It's case-sensitive comments, or they have block comments and stream comments. White space is ignored. Okay, and then I started getting into some examples here. Okay, so this is the part I'm going to emphasize this a little bit. So I mentioned that when you create hierarchical designs, there is an unfortunate side effect, which is that signals, the same physical signal gets connected, it gets named different things at different levels of the hierarchy. Okay? So in this case, I've got a top level design which is called NAND 3, and inside that I'm instancing an inverter and an AND gate, and then I'm connecting stuff. Right? Now it's really important that you get used to this syntax. So when I instantiate the AND gate, I say dot A, that dot A represents the input A on the AND gate. And then whatever's in parentheses after that is the internal signal in the current scope that's connected to that port. So in this case, I've got an internal signal called A, because inside of the NAND 3, well, I shouldn't say internal, I'm sorry. Inside of NAND 3, I've got an input called A, right? So that A has a scope that exists within that module. And then I'm going to connect it to the port A on the AND 3 gate that I'm instancing. So that A, so graphically it looks like this. You've got A coming in, and you've got an A on this port on this AND gate, and then you're making a connection there. Okay? So that is pretty easy to see, because if you're in here, you've got A, and then you can drill down into the AND gate, and you still have A, and it's the same signal. Anything you change in here will be changed on the A input inside the AND gate, right? But it gets a little confusing, though, when you start to have something like this. You have the AND gate, and there's an output called Y. There's an output port, and we connect that port to an internal signal called N1. Now, you might say, why didn't you just use Y? Why make this needlessly complicated? Just name it Y. Then it's called Y everywhere. Well, we can't do that because both of these modules that I instanced in here both have an output called Y, right? And because it's an output, I can't short these together because then that signal will get double driven, right? So I can't name this one Y and this one Y. And all the connections, remember, are done through naming, right? So I do have a Y, which is the top level output of the NAND 3, right? So the top level output is connected to the output of the inverter, which is happening like this, right? So the inverter has a Y output, and I'm going to connect that to the top level output Y. But the output of the AND gate is called Y, but I connect that to something called N1 internally, and then that N1 is connected to the input of the AND gate. So that wire, the point of all this is that because I named that, I have the N1 is here and N1 is here. That creates a wire inside the block diagram. So in my structural description, I have effectively drawn a wire. I've connected those two things together just because I used the name N1, the common name N1, that's connected to both of those ports. Make sense? Okay. Okay, and then so then I simulated this, and you can see I've got a counting sequence where I went through every possible input value. There's only 8, 2 to the third power, because there's 3 bits of input, and then the output is behaving as expected. And that's important. It's as expected, meaning that when I simulate this, what you're doing is you've got some idea of what you expect to see here, right? You say, well, I'm designing something, I know how it should work, and then I want to look to see how it actually works, and hopefully those match up. If they match up, that means it's working, right? So you have an expected value and an actual value. So when eventually when I write a test bench for this, I'll have something called expected Y and then actual Y. The expected Y is a value I'm going to just type in manually myself, and the actual Y is what's coming from the component. So the whole idea, and this is how you test all these designs. You look, like if you design your CPU and it doesn't work, you have to start drilling in, looking at waves, and making sure things are as you expect, right? So the methodology that you'll use is like you'll have your RISC CPU, and you'll simulate it, and it's supposed to be running a program that puts values out on the hex displays. So you simulate it, and you see X's or Z's for the hex displays, right? I think you'll actually see X's because if the input is Z's, the output would be X's, I believe. I don't know, whatever. You don't see what you expect. It looks like it's broken somehow, right? So what do? Well, you have a choice. You can either start at the beginning and say, all right, let's look at the clock. Do we have a clock? Because that's my heartbeat. All right, I got a clock. Okay, now the next step is, do I have a sequence of instructions coming out? Okay, I've got that. I look at the ports of the register file, or the right sequences of registers being written and read. And so you can start like that, or you can start from the end, and you can look at the wiring to the hex displays, and you can trace it back to whoever's setting that and figuring out why it's not setting that, right? And go backwards. Does it make sense? Okay. So the whole idea is that you're looking at the waves, comparing what you're seeing to what you expect to see there. Okay, and then there were some syntax things we covered last time, multi-bit signals. I pointed out that when you declare a multi-bit signal, you put the bit range before the identifier, which is different, than what you're used to. And I often forget, and I put it after. Notice too that every time you want to have, say, a 4-bit signal, you have to say 3:0. So you take the number of bits, you subtract 1, and then you put a :0 behind it. And then there's this idea of a conditional assignment, which is the ternary operator. I mentioned this is available in Java and C++, although it's not very commonly used there, but it's very commonly used in Verilog because it's used to create a mux. It's a really easy way to create a mux. The little ternary, so you have the select for the mux, ternary, and then followed by the 2 inputs. And you might say, what if I want a 4-input mux? What do I do then? You can cascade, or you can embed them. So you can take this part, the false part, right? And you can embed another ternary operator in there. So ternary operator only accepts 2 outcomes, right? But you can embed, you can create a nested ternary operator. So the way you would do that is, generally the way you do that is you'd put a new line. You'd have colon, new line, and you go to the next line and you'd have the next condition, question mark, outcome, colon, new line. So you can usually embed it, but you can format it in a way that looks nice. That's what I'm trying to get at there. Okay, and then internal signals are just declared as logic. Now there are other data types. There's integers. I think they have real, or maybe I'm thinking of that's VHDL. There's a bit data type. Don't get confused by that. We're just going to use logic in this class. The only other data type we'll use is integers, and those will be only for test vectors for test benches. So there is an exception to that where we'll use an integer data type. But that's only going to be a non-synthesizable code. So what I mean by that is when you write Verilog, you can write Verilog with the intention that you're going to convert it to hardware. And if you do that, you can only use a subset of the language, right? There's certain things that you can put in there that are valid Verilog, but that will disqualify it from being converted to hardware, right? Like, for example, the aforementioned, I want to set this to week 0. You can't, that doesn't make any sense. You can't create hardware that does that. I mean, you can, but only the transistor level, right? The logic is not compatible with that. Likewise, you can put like a wait statement in Verilog that'll cause it to wait a certain number of ticks, but that's only for simulation. You guys with me? So when you write Verilog with the intention to synthesize it to hardware, you have to be a little bit more careful about the only putting in there synthesizable Verilog. Whereas if you're writing a test bench that's just for simulation, you could put other things. So this logic data type is part of that. You want to stick to logic if you're using synthesizable code. Yes?
But isn't, for example, delay can be synthesized like a stack of inverters? So if there is an even number of inverters, then you get your original signals and you get the delay.
Yeah, like a ring oscillator. Yeah, that's, I've never tried to do that, but that would be technology dependent, right? So if you built a ring oscillator on an FPGA, which I've never done, and I don't know how that would end up. I've done it on an ASIC before, and I've done it using SPICE, it's transistor level circuit simulation. We used to use that as a trick to find out how fast, like we'd get a new process. Say, oh, we got a new technology library for AMI quarter micron. Let's see how fast it is. Ring oscillator, go. And it would see how fast it would oscillate. I don't know. That's a good question. But even if you did do that, you wouldn't be able to say, you'd have to tune that for the FPGA, the technology. So it wouldn't be something like, I want you to wait for 5 nanoseconds, so I'll put in a 7-stage ring oscillator. You'd have to test it. But I don't even know if that would synthesize. That's a good question. I should try that. It's a good idea. Just try one of those. There's something called a physically unalterable function, PUF. And that's a new area, actually it's kind of old now, I guess. It's an area of research that is attempts to put something like that, some kind of technology-dependent structure that actually has timing information that you can use to fingerprint a chip and determine whether it's fake or not. So if I make a chip, I can put a circuit on there that has a delay that's linked to the technology, the fabrication process, and then I can measure that delay somehow in terms of clock cycles. And then if that delay if someone made a knockoff of my chip, I might be able to tell because their ring oscillator is not the same speed as the original ring oscillator. So that's a PUF function. But anyway, it's getting on a sidetrack. Okay, so I talked about operators. These are pretty standard operators. The only thing you might not have seen before is the arithmetic shift has there's a regular logical and arithmetic shift operators, and that's necessary because of the fact that we don't have signed and unsigned types. Remember, everything's logic, right? Okay, so this is, I think, where we ended up. So in C and Java, you just generally work with a few different standard native data types, right? Usually 32-bit integer or 32-bit float, 64-bit float, right? But when you design hardware, you can specify how many bits every signal is because you're physically creating wires for those, or registers, or memory locations, right? And so I showed you how to do that. You declare them as logic, say 3:0, that's a 4-bit signal. But whenever you specify a constant in your code, you have to do that as well. Because if you just put like 3, the compiler is going to look at that and it's going to like, oh yeah, but how many bits is that 3 in, right? So there's a way to do that in Verilog, and and if you're a careful Verilog programmer, which you should be, because otherwise, you can run into some weird errors, unexplainable behavior sometimes. You should be careful when you write your code, and part of that is whenever you have a constant, you should specify its width in bits, right? So the way you do that is use the apostrophe. So for example, you'll say 3 apostrophe, and then you put your constant, and that means it's a 3-bit constant. Whatever follows that is the value, but it's going to be in 3 bits. Now the value can be in decimal, octal, hexadecimal, or binary form, base. So in binary, you'd put a B there with the number. So if you put 3 apostrophe B101, that's the value of 5 in decimal, or 101 in binary, right? Now keep in mind though that you might look at that and say, wait a second, why doesn't the compiler just count the number of bits? Obviously it's 101, that's 3 bits. Yeah, but for example, if you had put 1 there instead of 101, just 1, it still would have made it 3 bits because it would have padded with leading zeros, right? So if you put 3 apostrophe B1, that is actually going to become 001, right? Now you can also put underscores inside of constants, and those are ignored by the compiler, but they're useful for when you want to put little fields. Like you want to put them in for readability purposes. Like you want to split a constant up into different sub-sequences, you can stick an underscore in there. So if you see an underscore, the compiler just disregards it, but it allows you as a designer to make the code more readable. D is decimal, so 3 apostrophe D6 would be 110 in binary, right? And then hex is H, 8 apostrophe H AB would be 8 bits with the hexadecimal value AB. And then O is octal, but that's in my experience, you never use the octal. Octal is 3-bit characters from 0 to 7. If you just put a constant in, like 42, and you don't specify the width or the base, the default base is decimal. So this would be interpreted as a decimal 42. And the default, now they say unsized, but I believe Modelsim defaults to 32 bits. Now, what ends up happening though is if you don't put the width, generally what will happen is you'll be okay because whatever the compiler will figure out the width from its context. So if you assign it to a 4-bit number, it's going to take the least significant 4 bits and put it into that, or it's not 4-bit number, sorry, a 4-bit variable, 4-bit signal. It'll infer that you only want the rightmost 3 bits, right? But it's still better to always specify your bit width whenever you have a constant. That makes sense? Okay. Okay, now this is the part I think is always kind of fun. This comes up a lot. Bit manipulations, or sometimes called bit twiddling, is when you want to create a value by mixing and matching bits, right? So in this, you'll see this a lot. Use curly braces to basically concatenate multiple things into one value. Now when you do that, the ordering is always most significant left, least significant right. So it's what you would expect. So if you take, for example, if you say assign y a curly brace, you say a 2 down to 1, bits 2 and 1, comma, and then, and this one is a little strange. This is the syntax you use to duplicate a bit sequence. In this case, there's only one bit, b of 0. And notice I use brackets to slice out bits. So b might be more than one bit. B bracket 0 bracket is just the rightmost bit, the least significant bit. And then if I put curly brace 3 curly brace b of 0, that's going to take bit 0 of b and it's going to copy it 3 times. So I'm going to end up with the value of y will end up being a bit 2, a bit 1, and then b bit 0, b bit 0, b bit 0, right? Yes?
Why you need external curly brackets in this case?
That's the syntax, and you actually do need to have those external curly brace. That's just the syntax that the duplication.
Next A0 you don't have it.
Right, because I'm not duplicating.
Oh, so it's only for duplication.
It's only for duplication, yeah. You have to use those you have to use a double set of curly braces for duplication. But the outer braces are for the concatenation. But the compiler is looking for that syntax for duplication. So you can't do a shorthand and just say, if you just say 3, if you eliminate the outer braces, you'll get an error. And then A0, and then we have a constant, 6 bits of 100010, and there's an underscore there that's just ignored. So this is what you end up with. Everyone see that? Okay, so it's just syntax to get used to. Now this is kind of strange. You can actually do concatenation on the left-hand side of an assignment statement. So you can actually have the target of your continuous assignment statement can actually be a compound signal where I can, in one statement, I can take y and I can assign it into 2 bits of A and 1 bit of B using that syntax. Yes?
Why necessary should be 3 bit, or it can be 1 bit value? Why?
For the left side?
For the right side.
For the right side?
Yeah.
The right side, so in this case we're assuming that y is 3 bits. Obviously it's not 3 bits right above that, but this is a different y. I think I got this example from the book, but yeah, it's a little misleading because this implies that y is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits, right? Now this is, but it's weird though because sometimes you'll do this and it depends on where you're compiling it. Like Modelsim might be fine with that and it might just take the low order 3 bits of y and stick it in there. But then you put it through Quartus and it's like, oh no, you can't assign 3 bits to 12 or 12 bits to 3 bits, you know. So you should be careful. You know, you could just say y bracket 2:0 here and it'll just take the low order. That way you can explicitly select 3 bits out of y to assign to those 3. Okay, so I'm going kind of fast. If anyone has any questions, feel free to stop and ask. Oh yes, yeah, so here's I put this in here because you're going to have to, yes, you'll have to do this in the RISC processor. Sign extending, you learned about that in 2.12, right? Sign extending is when you go from one width, you convert a one width to a wider width, right? You take a signal that's 16 bits, for example, and you put it into a memory location that has 32 bits. Or you put it into an input on ALU that has 32 bits, right? Kind of a type conversion, right? If it's a sign number, if the original value, the original 16-bit value, for instance, was a sign value, you don't want to fill in the other bits with zeros because it'll change the sign. You guys remember that in 2.12, right? So you can do this, which is what I used to do. You can use the concatenation and say B15 is the sign bit, right, of the 16-bit value B. You can copy and paste that 16 times, right? Or you can use the duplication operator, and it's much nicer. I used to do it this way before I knew about the duplication operator. Yes?
What's with the comma B? What's with the B after it?
Yeah, so the idea is that we're going to take B is so this is kind of a it's kind of like a block of logic, but there's really no logic here actually. What it's doing is it's taking an input, which is called B, and the output is B underscore ext. B is a 16-bit number. B ext is a 32-bit number where you've sign extended. So in order to form that, the way it's happening here is we're taking the original B15. So this was the sign bit of the input. but on the output, the sign bit is B31, right? But on the input, the sign bit is B15. So we take that sign bit and we reproduce it, duplicate it 16 times because we want to extend the sign bit through the upper 16 bits, right, of the extended value. So in this case, the reason we add B is because we want to take the sign bits that we're adding in, and we want to put the original B value in there as well, right? So the original B value tags along. It goes through, but only in the lower part of the output, right? So the original B is now just the right side of the new B, essentially, is what's happening. Okay. Yeah, so I'm going to skip over that. Okay, so there's another thing. This is not as commonly used, but you may find this useful. There's this thing called a reduction operator in Verilog where it takes a reduction operator is when you take an array of values and make it one value. And so sometimes you want to take all the bits of a signal, of a multi-bit signal, and you just want to AND them all together, as if you had if you had a 32-bit signal and you put an AND in front of it, that will create a 32 input AND gate, and the output, that will evaluate to a single bit output. And they have reduction operators for AND, NAND, OR, NOR, XNOR, XOR, and XNOR, right? You might say, wait a minute, isn't the most useful reduction an add, to add a bunch of values up? Yeah, they don't have one for that. There's no reduction for add. But there is for, these are just, they have them here for logic operations. Okay, everyone okay with that so far? Okay, so now I thought I would go and do a little demo here where we can build some stuff, see how quickly I can get through this. If I think the TAs might have done a demo in the lab already too, but this way you'll get it from a different perspective. Okay, so let's start something here. Let's create something called an adder. And I'm going to I'm going to create a file called fulladder.sv. And so module fulladder. Notice the file name is fulladder.sv. The module name is fulladder as well, so they match. And I'll have logic input A, B, C in, and logic output S and C out, and I'll do end module. Okay, so there we go. I've got the top level design. This is similar to an example. I don't know if you guys, you might be able to read that. There we go. That looks better. Yeah, it's a little bit more readable. Okay, so so that's generally how I start a new module. I just start with the module line, and then I just leave it blank in the middle. Now, so far we've just basically, the only thing I've shown you so far is to do continuous assignment statements and structural Verilog. I've showed you those two parts of SystemVerilog. So we'll just do an assignment statement here. We'll just say assign S equals A XOR B XOR C, Cin rather, sorry. Wait, hold on, let me be consistent here. I'll call this Cin. So I have a C out, Cin, there we go. And then I'm going to assign C out to be A and B, or A and Cin, or B and Cin, right? So as long as, so the idea here is that if we have an odd number of 1 bits coming in, then the sum is 1. And if we have at least 2 1 bits coming in, the carry out will be 1, right? So you guys, hopefully you covered that in 211, right? The full adder. Okay, so I'm going to save that, and then I'm going to simulate it. So to do that, I'm going to do so the first thing you have to do before you simulate this is you have to compile it into something. I don't know what. Some kind of proprietary format that's used by Modelsim, binary format that's used as the input to their discrete event simulator. So to compile it, I'll do vsim full_adder.sv. oh, sorry, not vsim, Verilog, sorry, Verilog, sorry, scratch that. Sorry. vsim starts the simulator. Verilog compiles. Sorry, I was wondering why that was so slow. Yeah, Verilog. So I don't know what V is for. Log is for Verilog. So there's also there's another command for VHDL to compile VHDL, but Verilog is the Verilog one. It works for Verilog and SystemVerilog. Although there's some options I think you can add to define the dialect. But anyway, I just said vlog fulladder.sv, and I got an error on line. Oh yeah, I forgot the equal sign. Okay, thank you. Why is that? Yeah, and something about. Oh, also I put. Sorry. Okay, so a couple issues here. Number one, it should be input logic, not logic input. And output logic. Output logic. And also I forgot that equal sign there. Cout, assign cout equals. There we go. All right. All right, let's try that again. Okay, there we go. So, yeah, so it says compiling, 0 errors, 0 warnings. Now what that does is it creates a directory in here called work. Work is the library that module went into. So when you get into Modelsim, you'll see a library called work. Everything you compile will be in work. There's other libraries for other stuff. Yes?
That necessarily should be the case that the name of the module corresponds to the name of the file you are compiling.
No, it doesn't have to be, no. No, that's just conventional.
I see. And the files the Verilog creates when it compiles the source code is in the same directory as the source file, right?
Yeah, and that's a good point too. This often is a confusing thing because if I compile this, it goes into that work directory, and then if I log out and I come back in the next day, I got to make sure that I go to the same directory if I want to start using those compiled designs. So yeah, that's a good point. You should have a directory like for each lab, usually. In fact, we're going to give you a template, like a skeleton that you'll untar and you'll work in that directory. But you want your present working directory to be your project directory, because the work directory where your downstream stuff is going to be a subdirectory of that. Okay, so and if I go inside work, by the way, I don't know what the heck this is all about, but there's just some nondescript files in there that is the output of the compiler. Okay, then I use vsim. Sorry about that. So vsim add, what I call it, full adder, full underscore adder. Okay, then, so there's vlog and vsim, and you'll probably at some point get them confused like I did. But vlog is compile, vsim is start the simulator. And I screwed that up too. Okay, sorry. What did I do? Full or adder? Oh, sorry. Sorry, I should have just hit. Yeah, this full adder. There we go, full adder. Okay, so now notice I type vsim full adder. So from the perspective of Modelsim, that's going to be my top level design. The full adder may instantiate other modules inside of it, and if it does, you got to make sure you compile those before you simulate. So everything you need for your design, the whole hierarchy of the design has to be pre-compiled before you start Modelsim. And when you do start Modelsim, you start it on the top level. Now, I don't have anything in there, so I just have one module for now. Okay, so there's the Modelsim window, and let's see, can I make this a little bigger? Yeah, a little bit. View scale. Nope. View virtual screen. View. Hold on. Sorry, I'm trying to. It's not rescaling my. All right, well, we can work with that. Go to 150 and then actually let's do this. There we go. Yeah, there we go. Actually, I'm gonna resize to Okay, and then we go into scale mode. Yeah, sorry about that. Oh, that didn't work. Okay. All right, well, hopefully you can kind of make that out. Okay, so if you look over here, we have full adder, and this is going to be the hierarchy of the design shown here. And so when I was talking earlier about how signals have different names depending on where they are in the hierarchy, and you can drill in, you can view the signals at different levels of the hierarchy, that's what I'm talking about. I'm talking about this little pane. This little pane is where you do that. This becomes a tree, and you can browse through that tree. When you click on something in that tree, you're going to get all of the signals that are inside of that scope shown here, right? And then you have processes here, which is where eventually the always statements that we add later will be shown in here, which I haven't gotten to that yet. But when I do, those will be in here, and then there's a console down here. So if I want to simulate this guy, I can first take my signals here that are listed in the objects pane, and I can just right-click and say add to wave selected signals, and that'll create a wave window. And then there's a variety of ways now I can control the inputs. I can just type force A to be, say, 1. I can force B to be 1, and I can force C in to be 0. And sorry, C in, and then run. And I go back to the wave window, and you can see that I typed run, and the default run time here was 100 picoseconds, or 100. The resolution of the simulator is a picosecond, so 100 time ticks, or 100 ticks, 100 simulation ticks, 100 picoseconds, and you can see the waveform there. And notice how, if you probably can't read that in the back, but there's A, B, C, N, S, and C out there, and I've got strong 0 for adder A, or AA, strong 1 for B, and strong 0 for CN. So and then the outputs are just 1 and 0. So you can see what's going on here. The ones that I type force for are strong 0, strong 1, and the signals that are outputs of the adder are just regular 1 and 0, right? So does that make sense? If I put 0, 1, 0, I get a sum of 1 and a carry out of 0. Yeah, seems right, right? Okay. Another thing I can do is you can right-click on these guys. Oh, first of all, let me show you. You can restart it. Restart dash. Type restart. There's also there's some buttons here. You can use this button up here on the wave window to run. See how it says 100 picoseconds? This will run it. You can see because I restarted it and I ran it, I've just got Z's for my inputs and X's for my outputs. So flat lines. Blue is Z and red is X. The reset, this button is a reset button, and it just resets the simulation state. The other thing you can do in the wave window is you could do a right mouse click and you can say clock. So for example, A, you can set it up as a clock. So this has a clock of a duty cycle of 50 and period of 100. So just hit OK on that. And then right click on B and say clock, and I can set the period for this to be 200. And then for C, or C in rather, right mouse click and go to clock and say 400. And then I can, so that the clock is set up, and then I can run it. And you can see it creates a counting sequence for me. So if you look at C in, that was the longest period, so you can see that from 0 to 400 picoseconds, it's gone through all 8 input values and all 8 corresponding output values, right? Okay, so now let's say I want to start doing a bottom-up design with this. So I'll go back to the editor window here. Let's create something called, let's see, split. Let's create something called add8.sv. And so module add8, input, logic, 7 down to 0, A, and then input logic, sorry, output, input logic 7 down to 0 B, so those are my two inputs, and then I'll have output logic 7 down to 0 S, and module, there we go. And then we can have, to create some structural code, so full adder. Okay, so now I'm going to instance the full adder. Usually what I do for this is I'll start out with just putting the inputs and the outputs of the full adder. So A, B, CIN, dot CIN, dot S, and dot Cout. Okay, so I've got, let me put some new lines in here. Format this a little nicer. And yeah, there we go. So now I've got the full adder. Oh, I need to give it an instance name too, so I'll call it F0. Okay, there we go. So, okay. So I just pretty much just set up the ports for that guy, right? And then if I'm going to use full adders to create this adder, I'm going to need to have a carry chain, so I'll have an internal signal called carries, logic 7 down to 0 carries, and then I'm going to assign carries of 0, which is the least significant bit of the carry chain. I'm just going to set that to 0, right? And then for the adder, I'm going to take A of 0, sorry, bracket 0, B bit 0, so I'm going to strip off those 0 bits on those guys. Carry in will be carries of 0, S is going to be S of 0, and carry out will be carries of 1. You see that?
Yes.
So I'm going to take 1 bit of the 2 inputs, 1 bit of the output, and then I use 2 bits of the internal carries signal. And then I'm just going to take this and I'm going to paste it 3, 4, 5, 6, 7, 8 times. And then I have to just update the names of the instances and the bits. So this is bit 1, this is bit 2. Now, as you might imagine, there is a better way to do this. There's something called a generate statement that allows you to automatically instance an array of things. But for now, I'm just going to do it manually. 3, this is 4, this is 4, 4, 4, 4. Let me know if I make a typo here too, please. 5, 5. Yeah, I could have done that. I want to. Where I'm going with this though is I want to connect these guys to the board lights. So I want it to be. I don't want it to be 2-bit. So 5, 5, 6, 6, 6, 6. 6, 7, and then last one is bit 7. 7, 7, 7, 7. Now for the last carry, I'm just going to drop it. So I'm just going to leave that blank, and you can do that. So Cout is just not connected to anything. Inputs have to be connected, outputs don't. If you don't need an input, you can hardwire it, set it to a constant, but they need to all be connected. Okay, so we'll save that, and let's see if it compiles. Vlog add 8.sv. Okay, so I did get an error here on line 48. So, I forgot the parenthesis, yeah. I forgot the ending parenthesis there. There we go. I hope I didn't do that everywhere. I didn't. Okay, good. Yeah. Okay, compiled. So now I can do vsim add 8. Now I don't have to recompile the full adder because it's already compiled. If I had changed, if you change anything though, you have to recompile the modules if you make an update. But you can also do that in here. If you go over to the library tab in Modelsim, these are all the libraries we have, and you'll notice we've got a bunch of simulation libraries in here for the Altera FPGAs. But there's work, that's ours. So if I go to work and expand that, hit the plus sign there, I can see I'm sure you can't read that, but it says add 8 and full adder there. And if you right click on one of those, there's an option there to recompile. So you can say recompile. And so you can recompile it either in the command line window, like I'm doing there in the shell window. You can do it. You can also do it in the console here for Modelsim. You can type vlog space, full adder, or you can do a right click in the GUI. There's several different ways you can do it. Okay, so are we simulating? What are we simulating here? We're simulating the add 8 right now. Actually, I'm doing both. I guess I have two Modelsim windows open. So I'm going to take these guys, the inputs and outputs, and add them to the wave. Oh, also notice if we go back over to the sim window. Hello. Here we go. If we go back to the sim window, notice now I have a design hierarchy. I've got add 8 at the top, and then I've got all the full adders below it. And if I click on any of those full adders, I will get the signals that are in there, right? So I can now access the different levels of the hierarchy. And then, so I can say force space. Oh, also, instead of typing force, you can also do a right mouse click on the wave window. So I can right click A and say force in here. And I can just say 8 apostrophe D45, for instance. And then B rather, I can say right click and say force 8 apostrophe D10. And then I can hit run, the run button there up here. And then there we go. Now I don't really know what this is saying, so I can right click these and say format, radix rather, decimal, right? So you can see I've got 45 for A, 10 for B, and 55 for S. So the adder appears to be working. Everyone with me? Okay, so now I got it simulated. Now I want to deploy it. I want to put it on the FPGA now. How do I do that? Well, I just need one more. I need to build a wrapper. So I need a new top-level design that will take this design and will connect it to pins on the chip. So I was thinking that I could connect so I've got 8 bits of A, 8 bits of B, so I need 16 input bits, and then I've got 8 outputs. So I was thinking I can connect the inputs to the switches and the outputs to the LED lights, the LEDs, and then I can physically interact with this adder. Okay, so to do that, it's I want to go and let's create a new design here called top.sv. And so module top, and we'll have input logic. The inputs are the switches, which is SW in caps. And there are 17 out of 0 because we have 18 switches. Now you might say, how did you know that's what they're called? How did you know it was SW? It's actually written on the board in the silkscreen layer. So if you look at the board, you can see it actually says SW0 through SW17. It's really tiny, but it's on the silkscreen layer. And then let's see, I want output logic 17 down to 0. What are the red LEDs called? LEDR. LEDR. Okay, end module. Okay. Don't need that indented. Okay. Okay, and then so now I just need to create an add 8. I'll call it my adder, and again I'll just say .a, .b, .s. And then I'll fill in what I want in here. So I'll put A will be SW. I'm going to bit slice out 7 down to 0 for that. And for B, it will be SW 15 down to 8. So A is the rightmost. Actually, you know what? Hold on. A should be, sorry, let's make A 15 down to 8. And we'll make B 7 down to 0. That makes more sense. And then S is going to be, dot S rather, is going to be LED R 7 down to 0. Right? Make sense? Okay, now you might be thinking, wait a second, you're not actually setting anything into the other bits of LED R. So what do you think is going to happen to those? Well, the design doesn't set them to anything. And when I deploy this on the FPGA, they're literally not going to be connected to anything. They'll be floating. Yeah, they'll be Z state, but how is the LED going to, what's the LED going to do? Is it going to...
Well, we should look in docs for default states.
Yeah, we could look it up. One thing but it'll probably be, it's floating. It'll probably be like dim or something, right? On, but dim, right? But we'll find out. Let's see what happens. Hopefully it doesn't smoke it. Okay, so we good to go here? I think we're good to go. Okay, so I'm going to save that. Now, I don't want to simulate this, though. There's no point in simulating this in Modelsim, because Modelsim doesn't know what the hell any of that stuff is, switches and LEDs. We need to synthesize this now. So I'm going to start up Quartus, which is the tool we use for that. This is a separate tool. So you'll see this thing come up, and oh, it's pretty fast. Okay. And File, New, Project. Create a new project to hold all this stuff in. Come on. Okay, next. What's the name of the adder? It's fine. That's fine. Empty projects. Okay, good. And good. Okay, so we got a new project. And the first thing we need to do is tell Quartus what FPGA we're targeting. Now, believe it or not, there's a whole lot of these. They make a lot of different versions of the FPGA. So you're going to want to go into Assignments, Device first, and you got to find it. So this is a Cyclone 4GX is what's on here. And actually, if you can actually read the part number right off the chip and just type it into that name filter. But I'm going to do it the hard way. So I'm going to say package. I'm going to filter it by package. So FBGA, which stands for flip chip ball grid array. Pin count. I think there's 672. I think that's right. Oh, it's not the GX. Sorry, scratch that. It's the 4E. Sorry. Yeah, there we go. Sorry. 780. Yeah, I knew that pin count didn't look right. And then the speed grade is 7, I believe. Okay, so even with all those filters, I got a whole bunch of options here listed in this thing down here. I think it's this one. No, hold on. I think it's this one. EP4CE 75F29. I can confirm that by reading it on here. EP4CE 115F29 C7. Yeah. So I just.
That's down.
Oh, right here. Yeah, thank you. Yep. Oh, yeah. It's the 115. The 115, by the way, stands for 115,000 gates. That's the capacity of the FPGA. You might say, well, that doesn't sound like a lot, but remember, these are not 2 input gates we're talking about. These are 7 input gates. So you can pack like a truth table of 7 inputs into one of these gates, and then there's 115,000 of them. All right, so I'll hit OK on that, and then the only other thing I got to do here is I have to import assignments. Well, I got to bring in the source code files too, but there's a file. Now, you guys, I don't think are going to have to actually do this step because Charles has set up is going to set up a template for you. He's going to give you the project file for Quartus, so you can just open that project file, and these pins will be in there for you already. But since I started one from scratch, I'm going to import the assignments from, there's this QSF file. It basically just tells you, it just matches up the names like switch 4, right, to the actual pin on the FPGA. So that's all that's there. So I'll bring that in, and you can confirm that that worked by going to Assignments Pin Planner. And it actually shows you, this is the bottom of the FPGA, these are all the pins, and if you look down here, you can see for every one of those pins, there's a symbolic name that you can put in the, now these names, all you have to do to connect to a pin is you put in the module line for the top level design, you put one of these, or any one of these, names in the module line is the top level inputs and outputs, and that will automatically connect those to the appropriate pins, right? So for example, if I scroll down here, or actually I can just do a search for switch, you can see my switches are there, and you can see what the pin location is for each of those switch bits. And obviously that depends on how they soldered, how they built the board, right? Okay, so I'm going to close that. That was just for confirm. And then the last step is I'm going to go to Assignments, Settings, and I'm going to import. I got to go to Files and just bring in the. Oh, look at that! You can just hit Add All. Add All brings in the. Yeah, so we're good to go. There's the adder, and oh, the top level design. What's the top level? Sorry, one other thing I almost forgot. The you have to tell it what the top level design is somewhere. General? Yeah, top level entity, top. It put adder in there because that's what I named the project. Obviously, I don't have anything called adder, so top. All right, now we're good to go. Let's try it. I'm gonna hit the go button. I hit the go little play button at the top, and now it's gonna synthesize. And hopefully this doesn't take too long. I think this should be pretty fast because it's a small design. But I'm also running this on a laptop and a virtual machine. But it shouldn't be too long. You can see it's going. You'll notice that when you run these, you tend to get a lot of info messages. Sometimes you'll get warnings. There's a little timer down here. Here we go. Got some errors. Okay, so double click that. It brings up the editor. What did I screw up here? Oh, forgot a bracket. There we go. All right, save that. Run it again. If you double click on this, you'll get an editor window, or you can use your own editor, like I use Vim. Charles recommends, there's an editor called Visual Studio Code, VS Code in Linux. It's really nice. Or there's Sublime. I think Austin has Sublime in the labs. Atom, yeah, Atom's good. I like Atom too. Come on. You can do it. Meanwhile, while that's going, I'm going to check and make sure I got a connection to the board. So if you hit this button here, there's a programmer button. And so this is the programmer. And if you click Hardware Setup, you're going to see USB Blaster. I double click that. And then if you hit Auto Detect, it should detect it, hopefully. It should detect the FPGA on the JTAG chain. Yep, it looks like it did. I want to select the EP4 CE115. So there's multiple things on the JTAG chain. I guess. I don't know. I don't know what. I think one of these is one of these chips on here is the flash chip where you can actually burn. You can take an FPGA configuration and you can put it in a non-volatile memory. So that way, when you power the board down and you power it back up again, it will automatically revert back to the old, configuration. The way I'm programming it now, I'm programming it directly in the FPGA, so it's volatile. So if I unplug it, it'll go back to its, and plug it back in. I'll lose my design on there, right? But I'm gonna select this one. It's got 115. That looks right? Because I'm looking for 115. That's the numbers in the FPGA, and hopefully that will come up, and hopefully I won't get any errors in the compile, and we'll be good to go. Yep, there it is. Okay. So there's the chip. It found the chip. This TDI and TDO, that's the JTAG signal name. It's the same signals like if you plug in your your phone. Use the debugger on your phone. It uses JTAG. So it's a bit serial interface. And TDI stands for test data in, and that's test data out. So it's like a big shift register. Shifts data in, shifts data out. And holy cow, this is taking a while. Come on. It's done. Okay, good. All right, so now that it's done, I want to program that. Now the thing you're actually programming on there, it puts it into this output files directory. And the name of the file is, it's a SOF file. SOF is the bit stream. That's the file that actually goes into the FPGA and makes your hardware come to life. SOF stands for Serial Output File or something like that. So I double click that, and so then I click program, turn on program, and I hit start. Now what'll happen here, let me see if I can switch the document camera here. Yeah, oh cool. All right, so you'll notice that when you power this on, it goes through this, this design that's doing this, by the way, is on the flash memory. You could, in theory, change its behavior, like when you plug it in, like when you turn it on. I think I've done that, and it's been a while. I've done it before. I don't remember how to do it. But obviously, there's no reason to do that. But so anyway, when I program this, I'm going to hit the program button, and it takes some time. Now, there it goes. So now you can see it's reforming the logic. Okay, and it should. Is it done? Nope, still going. 37% done. So what you'll see on here on the programmer is, okay, there it is. So it's 100% successful. You want to look for this thing here when you program it, and so go back to the document camera here. Okay, so now what should happen is, remember, well, I guess I was wrong about the LEDs. They're just all off right now, including bits 17 down to 16, which I didn't connect to anything. Okay, but remember that A is now the first 8 bits and B is the second 8 bits. So let's put in 3 plus 5, right? So I'm going to put 3. So that would be switch. Oh, sorry, I messed that up. I want to go switch. So I say 16, it's 8 bits and 8 bits, sorry. So 9 and 8, right? Okay, so I'm going to flip switch 9 and 8 because that's the least 2 significant bits of A. And B is down here, so if I put, let's say, 5, 1, 0, 1. So this should be adding 3 plus 5 is 8, and 8 represents 1, 0, 0, 0. You see how it's hard to tell because the, yeah, you see that light is on. So I've added 3 and 5. Let's add 7 plus 5 is 12, 1, 1, 0, 0. So binary 12. And add 7 plus 7 is 14. 1, 1, 1, 0 in binary, right? So I've got an adder. Yeah, so that's basically it. Now notice that this guy hasn't changed because I didn't actually connect any of the pins that go to this LCD display. You can do that if you want. Likewise, I didn't connect to Ethernet or VGA or the audio chipset or the USB. Also notice, be careful here when you program your board, make sure you plug into the leftmost connector up there. That's the USB blaster. The other one is for if you actually want to program the FPGA to implement a USB host. And if you want it to be a USB device, like a slave, then you use the third USB plug to the right. But the first one is for programming. That's the blaster, that's the JTAG connection, that's your debug program connection. And also make sure that there's a switch on there somewhere. Oh, this switch. There's a switch that you want to always be in run mode. I think the program mode is for programming that flash I was telling you about. You want to have it in run mode. And likewise, I didn't use any of the buttons, but you're free. Oh, and there's also memories. So basically, whatever you put in the top level, you have your top level design. Whatever you put in the module line determines which of the components you want to communicate with on the board from the FPGA. All right? Okay. Alrighty, so let's head back to the slides. Any questions about that?
What is the second USB? Like first when you program insert for the USB slave and what?
Yeah, the first one is, it says device. Oh, I'm sorry, I had it wrong. I had it backwards. The first one, the one here is, it says device. That's if you want to if you want this to be a slave. The second one is host, if you want it to be a host, the master, right? Yeah, and then there's audio, VGA, so. But again, whatever you want to talk to, you just have to create a pins for that in your top level design. Okay, so let's go back to here. Make sure I covered everything. So simulation, talked about, wait, that's not simulation, that's, oh yeah, it is, yeah, it's Modelsim. Yeah, first time you bring up wait, why am I showing Modelsim though? Okay, sorry. This screenshot is anomalous. It shouldn't be there. Okay, so vsim, the Modelsim window, I explained that. I showed that. I showed that. Oh, I didn't show that actually because when I simulated Modelsim, I typed vsim space top level design. The other way you could do it is you could just start Modelsim by itself, and you can go to this. You can go to on the menu bar. You can say Start Simulation, and then you can point it to something in your work library and use that as the top level, and then just hit OK. Okay. This enable optimization you want to turn off if it's on, because if it's on, it'll hide the internal signals of some of the internal modules. Let's see, the Modelsim windows, I went over that. Design structure, yeah, I think I covered all that. Okay, in this slide, I have a few commands for Modelsim. So I showed you the force command. Now, normally, when you test, you're not going to be using force commands. We're going to use a test bench, which I'll explain in the next lecture. A test bench is when you write another Verilog module that'll actually take care of setting the inputs, right? And then also ideally checking the outputs as well. You guys with me? So you'll have another Verilog module that will be driving the input values. But if you want to do a quick and dirty simulation like I did, you can use these force commands, right? I showed you the run command, and then there was the clock. I did the clock through the GUI because I can never memorize this. This is the command line. This is the command window, the command line version of how to set up the clock, the oscillating signal. I can never remember that, so I always do it through the GUI. But that's the syntax of it. Anything you do through the GUI will show you the corresponding command in the command window. Here's a script. You can write a script called a do file, which just scripts out commands in Modelsim. And then to run it, you just type do space in the file name. Or you can go do it over the file menu. And then Quartus, I think I showed you all that. The editor has a really annoying autocomplete feature. It doesn't work very well, so I usually recommend that you turn that off in Quartus. I didn't do that because I didn't use the editor. I used Vim to edit my code. I just used Quartus to compile and program the FPGA. And then that assignments file I told you about is here on the lab machines, but you shouldn't have to load that in because we're going to provide you with a project file that you can use that will preload those assignments. You guys with me? So I don't mean to confuse you. If you start from scratch, you need to get the pin mappings, but you shouldn't have to do that. And there's the pin mappings. Okay, great. And then next topic, which we'll cover next time, is the Verilog process, otherwise known as the always statement, which will then allow us to also cover the test bench functionality. And I think that'll be pretty much all of the SystemVerilog content. You guys will be in good shape. Okay? Great. Okay, thank you. See you next time.